Hi everyone, this is Maths4Uni. This is question 1 from lecture 10 of our Udemy course, Bridging the Gap to Maths at University. If you find this content helpful, then please consider liking and subscribing, as well as checking out our full Udemy course. The link is in the description. The question says, prove the Cauchy-Schwarz inequality for the dot product of vectors. There is a hint, which is to proceed in the same way as we did for integrals in the corresponding video in the course. So for starters, what exactly do we want to prove? We want to show that a dotted with b all squared is less than or equal to the modulus of a all squared times by the modulus of b all squared. This is the Cauchy-Schwarz inequality. If we proceed as the hint tells us to, as we do with the integral result, we consider a minus lambda b dotted with its self, where lambda is an arbitrary constant. We notice that this expression is greater than or equal to 0, since when you dot a vector with itself, you have the square of that vector's magnitude, which is non-negative. We assume that b itself is not the 0 vector, since if it is, then the Cauchy-Schwarz inequality is true because you'll get 0 on both sides. This assumption will be helpful in a moment. Next, we expand this out over the dot product that we have in the middle. This gives us a dot a minus lambda b dot a minus lambda again with an a dot b, and then a plus lambda squared and then a b dot b. And this whole expression is greater than or equal to 0. You might like to think about this, but the dot product is commutative, and so b dot a is equal to a dot b, and therefore this left-hand side reduces to a dot a minus 2 lambda a dot b plus lambda squared b dot b is greater than or equal to 0. We note that the left-hand side of this inequality is a quadratic in lambda. It is a positive quadratic, like y equals x squared, rather than y equals minus x squared, since b dot b is positive. We assumed earlier that b was not the 0 vector, and so therefore b dot b will not be equal to 0. So we have a positive quadratic in lambda. If we want a positive quadratic to be non-negative for all values of lambda, which we do since we haven't chosen lambda yet, so this inequality must be true for all arbitrary values of lambda, then this quadratic must have no roots or exactly one root. If it has 2 roots, then it will go underneath the horizontal axis if you picture a graph in your mind of a positive quadratic. We can phrase this discussion on roots in terms of the discriminant of the quadratic. The discriminant must be less than or equal to 0, since if it's strictly greater than 0, then there will be 2 roots, which we want to avoid. The discriminant of the left-hand side quadratic is 2 lots of a dot b all squared minus 4 b dot b, and then we have an a dot a. And this is less than or equal to 0 because we want to have no roots or 1 root. If we cancel the factor of 4 and rearrange, then we arrive at the Cauchy-Schwarz inequality that we wanted to derive. If we cancel the 4, we get a dot b all squared is less than or equal to a dot a times b dot b. We note that a dot a is the modulus or magnitude of a squared, and this is the same but with b. And so we arrive at the Cauchy-Schwarz inequality for dot products that we wanted to derive. If you found this content helpful, then please consider liking and subscribing, as well as checking out our full Udemy course. The link is in the description. Thanks for watching, and goodbye for now.